Okay, folks. So let's start with where we have left yesterday. We'll revise that what we have studied yesterday, and then see how virtual memory works. Uh, all right. So we have studied this thing in the last class, that very simple way of designing a computer system is that we have physical memory, and then a processor is connected to that, right? And processor directly accesses physical memory. So this kind of system is very primitive, uh, and it was used in earlier computers. And note that only one program can use such memory, right? Only one process can use. uh, okay, and that's a limitation. And then if the process wants address space which is larger than the physical memory, then it cannot use it. So these are the limitations, right? So this is surely not in use until unless you want to create a very simple computer, embedded kind of computer, wherein requirement of memory is very less. Only one process runs on that controller, right? So that's possible to design, but no desktop computer uses this kind of stuff. And today's computers have 100 plus processes running all the time. It's managed by OS. Okay, and then we have multi-core processors, right? Uh, okay, and so all right. So there are hundreds of processes, and OS multiplexes these over available cores. There can be 4 core or 8 cores processor, and then hundreds of processes, and then OS just maps, or schedules these processes over available processors. But memory is just single one. Physical memory is just one memory. Okay, while we show here as illusion, okay, that each process gets. Okay, and then all right. So and then each process has its own address space. Okay, and we have looked at this address space. How when processor becomes active, or OS creates process then creates structure like this, right? That we have seen. And different processor may have slightly different way of structuring this, but in general is something like this. We have code, static data, heap, and it's like that we have studied in detail, right? Okay, so every process thinks it has all address space available, which could be, if it's 32-bit address, uh, you know 32-bit structure, or a processor is of 32-bit. Okay, then address space available is 2 raised power 32 in most of the cases, right? There can be exceptions, like one Intel processor has less address space, but nevertheless, so 2 raised, so each processor thinks that it has 2 raised power 32 spaces available. Okay, and okay, and this number could be very large, as we are moving from 32 to 64 and so on. Okay, all right, and each of these processor has to run in own address space. It means that each is the process has to have address 0000 0000, like here. It means that now, see, and let's assume right now that there's only one core or single processor. So there must be context switching. Means sometimes process one is running, then process two, and so on. Any process can run depending on what OS really wants. Okay, and but they have to reside in memory. Okay, all these processes which are running has to be there in memory, right? So they cannot be put, we cannot do this, that in main memory, when process, OS shifts from process 1 to process 2, then it removes everything from main memory and brings everything, because the whole thing is going to take hundreds of cycle, and it's not desirable, right? So it means that all these you know all these things is available in some part of it, or something is available in main memory. Okay, but processor has a view that everything is available in main memory. Processor doesn't care, right, whether it's available or not. It simply issues address, one of these address, and then it's left to then memory manager to do the needful. Okay, for example, process 1 may issue some address 05, for example. Okay, and this guy may also second process may issue also 05 and so on, but it has to map appropriately, right? And if so, these are the same, but it will should be mapped differently at different places in physical memory. Okay, so we have this now. Let's assume that we have one address space. Okay, and then what it is issuing is actually, this process is issuing is virtual address. Say this is virtual address. This is not the real address in physical memory. This is the view. What it issues is what it thinks that each process thinks it has complete address space, right? So it may issue whatever it wants, but actual fact is that this memory is between 0, 0, 0, 0 to some number. Okay, which could be very different from say for example, this is 2 raised power 32 size. This could be for example 2 raised power 16. It's possible, right? So but this, all this, not only this, but for all process it has to be put somewhere here in physical memory, which is DRAM memory or main memory. So there has to be some translator, okay, which will convert which physical address to physical virtual address to physical address, and we call this unit is memory manager. So we have studied this in last class. Okay, and then okay, so this is something extra I have brought in for your understanding. So we have virtual memory, okay, or virtual address, so the process view of memory, which we'll call virtual memory. Okay, and then physical memory, and this virtual memory exists for is there for multiple processes which are running on the processor, right? And there is a limited physical memory. Okay, and then what we do is that we both of these share the physical memory. This process A and process B share the physical memory. Okay, so now what we do is that we have concept of paging. We divide the virtual address space into number of pages. Okay, similarly we divide memory into number of pages. Now page is of fixed size for a system, for example, is usually around 4k bytes. Okay, 4 kilobytes. Okay, all right, and it means that now the size here and the size in virtual memory is the same. All right, and then as a result of that, now we, in this physical memory, we can put pages of different processes, right? So for example, this page here, page 0 corresponds to page 2 of virtual memory A, and then page 2 here in physical memory corresponds to virtual memory page 3, and so on, right? And similarly page 1 here maps to corresponds to this virtual memory page 5. Okay, any question up to this point?
No.
Okay, all right. So now we create this kind of table. Now note that this table, okay, which we call it page table, corresponds to each process. This means each process has a table which maps virtual page number into physical page number. Okay, physical page number. So here, for example, virtual page number is 0, 1, 2, 3, and so on up to 7, and we call this VPN. And the physical page number is which you call PPN is 0, 1, 2, 3. Okay. Now note that for process A, we are using go to previous diagram. See that we are using these mapping is as follows, right? So physical page 0 is mapped to page 2, and then this virtual memory page 3 is mapped to page 2 of physical memory, and this one 7 is mapped to 3. Okay, so now we can do the same thing here in the table. I mean, we can show this mapping, right? So we can, when we put X in front in a column, this column of ppn, it means that that page is not there. Okay, it's not valid. Okay, so valid is 0. Okay, valid bit. And we can see that now page, it means page 0 and page 1 is not here. Okay, then page 2, page 2 is mapped to page 0. So it means this page is actually, contents of this page are kept here. Okay, and then 3 is mapped to 2. So this 3 is mapped to 2. And then we can see page 7 is mapped to 1. Oh, page 3, sorry, this one. Okay, and so on. And this corresponds to another process which is not shown here. So we can see this mapping here. Okay, that we have discussed just now. And then for the second process, uh, this page 5 is mapped here. All right. Okay, any question? Now let's assume now process A wants some other page, because control because of instruction executed or data needed is somewhere else, right? Not in these 3. Then one of these pages can be removed and the page can be brought in. Okay, so this so one of the pages, let's assume that OS decides to, or MMU decides to take out this page, and then it will get, then the contents of this page are mapped here, or it goes to physical memory here. Okay, now the question that I may want to ask you is that while we are talking of this virtual memory, what exactly it is? It's the address space. See, as soon as you start a process, or OS starts a process, it creates this virtual space, right? It creates this mapping. Okay, and the structure of that we know is it has a stack and static and all code area and so on. Okay, but so it means that it has to exist somewhere, right? Where does it exist? We'll answer that, right? Now, modern processors, in modern processors, right, memory is not a constraint. Memory is huge. I mean, in even mobile phones, we have 64 GB kind of memory, and then bigger processors will have even large memory. So many processes can directly sit into it, and we'll see how. Okay, however, if the memory is limited, and of course, even if it's not limited, then there is all this that's created by OS has to be part of that, has to be in main memory, but rest of it, everything has to be there somewhere, and that we'll see. Okay, so today we have, see, there are two systems of doing virtual memory that we are studying. One is, first is called segment, using segments, and second is by page memory. So okay, we are not studying segment because it's not in use. Okay, however, your OS course will probably cover this. All right. Okay, this, all this we have studied. So now we have, each process has an address which is, in case of this is 32-bit address. Okay, so address space 2 raised power 32 size. Okay, so we call this as a virtual address, because each process can have 32-bit address, and each process may have same view of address space, right? So we call it virtual address. So virtual addresses we divide into pages that you studied earlier. So we show it this way. This is a virtual, we divide in two parts. One is called virtual page number, and second is called offset. So this is offset gives which byte we are reading inside a page. Okay, for example, load word says, so basically your load byte, it gets it gives address of particular byte. So processor issues byte address. Okay, so then this offset is required, which byte inside a page we want to read. Okay, and this virtual address now has to be converted into the physical address, right? Okay, so mapping is generally that, this what we do is that this using some translator, using page table, etc., we convert into physical page number, and we just take offset from here, same offset, and then we have actual address in physical memory. Okay, so basically there are three things that we can achieve. We get the illusion of very large memory which is private, which means each processing is a private memory available, and it's a uniform store. Okay, so now pages can be mapped differently for different processes in physical memory, so we can create protection. Okay, also we can allow sharing, because physical memory pages can be shared across multiple processes. Okay, which we have not discussed here. But what happens is that my question that I've asked is that the complete process, I mean, whatever memory addresses that we have seen, that from 0000 to FFFF in the address space is available, is kept. OS places that in secondary memory. Okay, say disk, for example, which we call it swapping store. Okay, so, or sometimes we call it swap space. Okay, all right. And in case there is and of course this is there is a mapping. So in case a page is not available in physical memory and process wants it and it's available in secondary memory, then it brings it to the physical memory, right? Okay, that we call it demand paging. On demand, you bring the page which is available in disk to main memory. Note that in the disk we have same structure process, OS creates. What structure I'm telling? I'm talking about oh, just a minute. I'm talking about this structure is created, right? All right. Okay, my pen again is gone. Okay, all right. Just a minute. Yeah, all right. Okay. So this structure we are talking of, this structure is okay there in swap space. All right. So this is actually cut into pages, and whatever is needed is brought from secondary memory to main memory. All right. Okay. All right. Let's go back to where we were. Okay. Now let's move ahead. Okay. So now we'll get into details. Uh, so we have a concept of virtual pages. So what virtual page is mapped into a physical memory, a page in physical memory that we have seen. If the virtual page is in physical memory, fine. So this mapping in the table is it to page in physical memory that we have seen just now, previous example. And if it is not there, then page is there in the disk. Then we map it to page in disk. Okay, so it's something like this. Okay, so virtual address we get from program. It has two parts we have seen, that virtual page number and offset. Now this total is called virtual address. Okay, and we use VPN to look into an entry, and then from there we get a mapping of physical page number. Okay, and use offset to find out which byte we are reading in that. Okay, now if this page is not there in physical memory, because physical memory is shared among many, then, and if the process wants a particular page, then we, there is a mapping of those pages which are not in physical memory in the disk, in the swap space, and then these pages are brought into physical memory. Specific, for example, this page is mapped here, which is not there in physical memory. That page will be brought in to this one. Any question? No? All right. So now, as we have seen, the structure of page table is as follows. We take the virtual page number, which you call as VPN, and this is a table, page table, which call it PT. Go to a specific, use this as an index, and go to particular entry in the page table. And if there is a valid bit is 1, it means that page is there in main memory. And then from here you get the physical page number. Okay, and then you use this to go to physical memory, and then this gives the offset. Okay, and this is actually what you get is location, particular location. So you take from this entry a physical page number and use offset, and then this gives you physical address. Okay, okay, all right. So this, when we say physical page number, is actually a starting physical address. All right. So we're not going to that level of detail. We are just saying that there is a mapping, right? So now what is this pointer? Physical page number is nothing but address where this page is starting in memory, and then offset is given by this. So we can find out particular byte using that. Okay. So this is the view. Now each process will have its own page table, and each page table will map into different pages in the physical memory or main memory. Okay, now it means that all the pages required by process one need not to be contiguous. Okay, for example, yellow pages are spread everywhere, wherever the space is available. OS can use that and map it to different processes. Okay, so it is non consecutive pages that can be mapped to. All right, so same point we are discussing here. Each process has its own page table. This is process 1, process 2, process 3. Each has its own page table, and each page table maps into physical memory, and of course it also maps into swap area, okay, which we have not shown here, or disk. If it's not available, for example, this a particular entry is there and this page is not available in main memory, then it maps to page in swap area. Okay, all right. Now role of OS is that OS keeps track of which process is active. Okay, so when a process switch happens, it means that the process which was non-active is made active. Then OS loads, or OS, basically gives a pointer to the page table of that, because each process has its own page table and somebody has to keep track of that. It's OS who keeps the track of that. As soon as OS loads a process, okay, makes process active, it simultaneously give pointer to that page table. Okay, so it chooses the correct page table, So and then rest of the process is that once page table is available, then we use virtual address, VPN, virtual page number as an index, and from there we get address of the physical page, and then use offset to get the byte. So same thing is shown here, that this is VPN, this is virtual address, this is VPN, this is offset. Then we have a mapping, this mapping virtual page number to physical page number, and then offset, and then this is actual physical address. Same thing we have shown here. This is virtual address split into two parts: virtual page number, offset. Virtual page number, there is a, we use convert to physical page number using page table, and then offset is taken as it is, and then both combined gives the physical address. Okay, all right. And then we have discussed this point also. Again, we will look into it. What happens if virtual page is not in physical memory? Then it must exist on disk. Then virtual memory system the page from the disk into page in physical memory and updates the mapping in the page table. So simple. Now look at this. This is a disk. Okay, and disk has the image of, disk has actually OS creates exactly same structure that we have seen for each process, right? So it has entries corresponding to the address space. Okay, so there is a, if address space has, okay, so here we have shown slightly different numbering. Okay, so basically there are, okay, what is shown here is actually when we have n bytes. Okay, and p is the okay, we so okay, all right, okay, is yeah, slightly different because I've taken it from different. So n will take same, n is total number of bits in address space. Okay, so number of bits to represent address space. So basically it could be 32, for example, and split into two parts. uh, this is page part or offset. We show this using p bits. So there are overall n bits in a virtual address, and then this is p bits for the page. So this is nothing but n minus p minus 1, n minus p, sorry. Okay, n minus p. So n minus p bits are used to represent pages. So now we have 0 vp0 to vp 2 raised power n minus p minus 1. So it's clear. Okay, and where is if you look at 2 capital N, which is nothing but 2 raised power n, total number of bytes in system. So basically this is the disk memory corresponding to one process. Okay, it has partitioned into 3 disjoint subsets. First is called unallocated. It unallocated are, you note here, which it means that these pages have not been allocated or created. Note that address space is quite big, 2 raised power 32 minus 1. A process may not be using all everything that's there in address space, right? Maybe using only few. Then, right, the one which are not used are called unallocated. Okay, and then we have cached. It means that when we see cached here, don't get confused with the caches we have used. A cache means that from disk, these pages are put into main memory. It means it is cached into main memory. The cache here is not a noun, it's a verb here. It's a cache into main memory. Okay, and third is uncached. It means that they exist, but because of space constraint, they are not brought into main memory. Okay, all right. So now you note that cached ones are available in main memory, like here. Okay, and uncached one are not brought into main memory yet. Okay, question.
Sir, can you please explain that p bits and n minus p bits.
Oh, okay, all right, okay. So basically, virtual address is 32-bit, let's say in our example, right? Okay, and then we divide this into number of pages, and each page is of, for example, 4K bytes, right? 4K bytes will require how many bits to represent each page? Offset within each page, we need 12 bits, right? 2 raised power 12. Okay, and remaining 20 bits are corresponds to virtual page number, right? This is offset within a page, and each page is 4K, so 12 bits are sufficient. So now this is what we call as P, or page size, is represented by P bits, and overall virtual address is of n bits. Then VPN will be of size what? 32 minus 12, that's 20, which is nothing but n minus P bits. Okay, so now this gives which one of the VPN number gives it points to a one page in virtual memory, right? So that's exactly we are telling. So in virtual memory, we have 2 raised power n minus p minus 1, and same thing, I mean, the virtual address space we divide into so many pages, right? Virtual pages. So same thing we are showing here, and with the memory we put everything. OS creates everything that is there, that's created for the process, into the disk or swap space. Okay, all right. Is it clear or not?
Yes, sir.
Okay, and forget about this n. N is nothing but we have considered total n bits in virtual address. Virtual address is of n bits. So this virtual address will point to what? 2 raised power n minus 1 locations or bytes, and there is nothing but we represent this as capital N. All right. So now let's move right ahead. So where do we keep the page table then? Okay. So right now we assume that it's in physical memory. It's part of the physics. It's there in physical memory, right? So we'll get into a more complexity. Can we keep page table in cache and so on? Because for every memory reference, if it's in main memory, you will lose hundreds of cycles. So anyway, we'll get into that little later. Okay, how to optimize this? So we have page table. This is page table. Okay, it's resident in DRAM. Okay, it has now the entry here. Okay, has two kind of addresses, right? First, of course, it could be null. It means that the entry does not exist. Okay, or it could be valid one. So the one which is shown as light blue is basically it will be mapped to physical memory. And secondly, something that we have shown here in the gray, it means that it's not there in main memory but exists in disk or swap space, right? So that's how it is, right? So we have disk memory. It has all pages corresponding to address space, so or virtual memory. Okay, so we note that we have 1, 2, 3, 4, 5, 6. Up. Okay, all right. This has how many? 3, 4, 5, 6, 7, 8. Anyway, its numbers are slightly, maybe 0 is missing. Anyway, it doesn't matter. So we have exactly all right, fine. So this disk memory, and then we have here physical memory. Okay, and then what we have done is that the pages that exist are mapped here, main memory, and the one which does not exist are mapped onto the disk memory. It means that the address here corresponds to disk memory. All right. Okay, any question?
Sir, what is the size of disk memory?
Which memory?
Disk memory,
This memory,
virtual memory.
okay, this memory could be anything, right? So there is a lot, see, lot of details right now we are hiding. Okay, and this memory can be in terabytes. So now you may ask that how do we actually map this address and all that? Okay, whether there is going to table, some other pointer, you know, all that details we are not getting into, right? So what we say is that whatever is there in, what do you call that, address space, and meaningful things which exist are mapped here. Now note here we have not shown vp0 because it's a null here. Okay, it means that it does not exist, so we have not shown this mapping. Similarly, the other null is not shown here, right, which is vp5, so it does not exist, so it's not mapped. Okay, so we are not getting into what is going to be the how address are represented inside a disk, etc., etc. Possibly you will learn all that in OS course, or you can look at how Linux behaves. So right now we will restrict our understanding to the fact that if there is something called swap space, all the pages that exist in the process are available in swap space. However, main memory or physical memory may not have all the pages, and this page table contains this mapping. And if something is not there in main memory, it is brought from swap space. That's all the understanding is, right? Okay. So, all right. So this is anyway we have already studied. So we'll not. Okay. So only thing is valid bit if, okay. Okay, valid bit is set, it means that it exists in physical memory. Its valid bit is not set. There are two possibilities. Null address, if the PT or page table entry contains null address, it means that page does not exist or it's not allocated. If it's a non-null address, it means the start of the virtual page on the disk. Okay, that we'll see now. So this is the case that there is something called page hit. It means that there is a virtual address given by process. Okay, uh, okay, it's already there. Okay, I thought it's not there. So look, go to the VPN and look at this, gives index of the page table, and then look at the entry. Okay, its valid bit is 1. It means that it exists in main memory. It means there is a hit now. Okay, second thing is that if it does not exist, which is called page not hit, then the page table entry, for example here, refers to a location in swap space on disk. So we'll see the next case. If there is a page fault, if it means the page is not there or not hit. Okay, and then okay, we have VPN. Take VPN, go to page table, look at the entry here. It means that now valid is not 0. It means that it's not there in main memory, and this address is non-null. Then go to what, using this pointer, go to disk memory, get this page and load it into physical memory. Okay, now in order to load into physical memory, one of these pages in physical memory must be evicted, and then we can use algorithm which will study in detail in OS course which page will be removed, and we can have least recently used, first this in, first out, all those techniques are there. Okay, which will study in OS course. Okay, so what happens is that okay, just a minute. So now this page has to be brought in, and one of these pages has to be evicted. Now OS decides that this page number 4 is to be evicted. Okay, and then this page is now brought into from secondary memory, like this page is brought into this location, which shows in the next page that now it's updated. All right. And this entry which was now pointing to, okay, so note that there is a change in entry also, right? This entry was pointing to page here. This is a virtual page number, whatever this virtual page number. Corresponding entry was, it was 0, and it means it's not in memory, but this address was non null, so it means that it's there. Now in the next case, when the page is brought into this place, then this entry will change, and the valid bit has become 1, and this has become non null, and actually it sorry, this will represent the address of this one. Okay, all right. And next time if the request comes for the same address, then there will be hit, because it will now is available here. It means that valid bit is 1, and that particular page is available at this place. So this process of bringing page from secondary memory or swap space to main memory is called demand paging. All right. Okay. Any question?
Sir, could you repeat what demand paging was again?
Okay. Whatever process we have seen, right? That something does process wants some location which is not there in main memory because the corresponding page is not there. Then this page like is exists in swap space, and this is brought into main memory on demand of the process, right? So that page does not exist in memory but exists in swap space or disk, then it's brought into main memory because it's required. That's called demand paging.
Sir, is swap and main memory disjoint, or is main memory a subset of the swap?
Disjoint means what?
Like, so, like, sir, imagine if it's cached, like a particular page is available in main memory. Is there a copy of it on the swap also, or is
Yes, 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 yes. Now we have you can look at what we have done in case of cache memories, right? When we say write allocate, write not allocate, we have written that into the main memory. Sorry, from main memory sorry, main memory also to disk. Actually we have not discussed that, sorry. So but so all right, so basically it's a one-to-one mapping in some sense, right? But now there can be methods, right? For example, okay, what I want to say is that for each process there is, what do you call that, we have seen this whole diagram, right, starting from 0000 to whatever FFF. So all this is created by OS, right, when the process is forked off or started, and then corresponding to these pages. So it means that now program will come also as a part of this in data area, and there will be stack and all this, right? All these are also the one which exists because the address was huge, must be copied or created. It is created also into the disk, which sometimes we also call as virtual memory. So it's placed in the swap area, swap space. All right. Now it's different thing that there is VP1 here is exactly replica of VP1 here. It totally depends on policies, right? Maybe at the time of eviction, this must be copied here, and so on. And swap space has meaning as long as process is active, otherwise it's removed from the disk, or when process gets killed, then it's removed. Okay, so there is a possibility, for example, process is doing a lot of writing, so it's gets written into this page continuously, but it's not gets updated here. This because it may not be necessary. When this page is evicted, maybe this is updated. So it totally depends on policy what OS wants. You'll study that in later next course. All right, is it, am I able to answer your question?
Yes, sir.
All right, let's move ahead then, right? Now, page fault, it means that if something that processor is asking is not available, and it has to be brought from a swap space, that's called page fault. That page is not there, right? And now OS comes into picture here, right? Because it has to bring that page from secondary memory to main memory, right? Okay, so memory management unit, if it happens, the memory management unit triggers page fault exception. Okay, it means that page does not exist now. And raise privilege level to supervisory mode. Now, this is a process of bringing the page from secondary memory and loading into appropriate page and physical memory is role of OS. Okay, so now from user mode, process is running into user mode because you have written a program and it's running. But all this transfer, because it's very sensitive information and user cannot do it, so it must be done by kernel or OS. Okay, so OS runs this. So page fault happens and OS runs this some program which call it page fault handler and brings the page into main memory. Okay, so it's like this, that page fault happens and it brings the page from disk to memory, and once this happens, the return to instruction that has caused the page. And since now whatever page was not there is available now, the next time there won't be any page fault. All right, so this is the process, right? I mean, once page is brought in, the control comes back to uh, same program that was running and same instruction is executed again. Okay, is it okay? So we call this the process of transferring page from disk to memory as swapping. Okay, um, so there are two words which I have not shown here. Is one is called swap in. Swap in is, it means that from disk swap space bring it to the physical memory. They bring a page from swap space to physical memory is called swap in. Swap out is that when the page is evicted and it's a dirty page, it means that something has been changed, bring it to swap space, right? So swap in and swap out. Demand paging we have already studied. And so there are a lot of approaches to predict misses and swap pages and all that, right? So a lot of optimization we'll study in OS course. All right, now interesting thing comes, right? So these are the page tables for different processes or programs. Okay, now VA1 here shows that same address can exist in each, for each process. Okay, and then each process is own page table. Okay, and the page tables are mapped into these pages in the page tables are mapped into the physical memory. That's what we have studied, right? Question is that now where does this page table reside? And what is the size of the page table? What is the size of the page table? Now let's take 32-bit address space, let's assume, and then page size is 4 KB. 2 raised power 20 entries must be there in the page table. Each page table has to be 2 raised power 20. It's huge. Okay, so you cannot keep it in cache. And each process has, this is the size, right? Process page table size. So so right now we assume we will optimize it later, but let's assume that we'll keep this in main memory. Okay, so space required for page table is proportional to address space and number of users, because each process will have a page table, right? And can be very, very large. So we can't keep it in register or caches. So it has to be in main memory. Okay. Now question is that how do we find this in main memory? First thing you know is that what we are trying to do is to go into page table, right? Each process has page table, and page table we say now is there as a part of somewhere here in main memory. So somebody must give its address. Who gives this address? So it's a responsibility of OS. So corresponding to each process, when process is created, is a page table is also created. The page table is there in main memory. Okay, and then OS keeps track of page table for each of these processes, right, or programs. And then when this process, for example, process 1 comes into picture or execution, then OS loads that page table starting address into something called page table base register. Okay, so it means it's a responsibility of OS to keep track of where the page tables reside in main memory and give that address and load that address into page table base register whenever process is in execution. Okay, so the process follows. Step 1 is access page table for the address location. So the process has given some virtual address, and then first find out where is the page table is. Okay, is the role of OS. And then the next step is that from page table you once we know the page table, then use the index and go find out physical page number and go to physical page number. Then so this shows the references here, right? This is a page table, for example, here. Okay, and use the index in this page table and get the address, right? For example, some address here. Okay, so basically it requires two steps. Now it's everything is slowing down, note, right, while your processor is still executing at the clock cycle speed. So it means that now we need to optimize all this. All right, so this okay, so all these page table, right, corresponding to process 1, process 2, process 3, this address must be kept somewhere, right? So there is another table which we call it kernel page table, this kernel page table, and that has entries corresponding to each process. So it will have process number, okay, process number and corresponding address. Okay, so now this gives you a little integrated view. You are creating virtual address here, a process creating virtual address. Okay, and then we have page table base address register. Okay, where does page table address register gets loaded? Okay, it's basically it gets this data, OS loads this from this kernel page table, which is also in main memory, right? So it loads corresponding to process number. Let's assume this process number P1, it goes to this page table kernel, and its base is given by another register called kernel page table base. And once it gets the value, it loads into page table base register. Okay, and then from this we have address of starting address of page table, and then use VPN number to index this. Okay, and then you get physical address, or if it's there, its page is there, and then you go to particular physical page and use this offset to find out particular byte in that. Simple. Any question? Is it complex? आ रहा है समझ में? Shall we go through it again?
Sir, the kernel page table gives us the base register, right?
Yes, kernel page table tells us where the page table of particular process resides, or basically starting address of that. Okay, now this has to be loaded somewhere, because now process, okay, it from that, for example, is for process P1. Then you go to kernel page table is shown by a kernel page table base register. Okay, or kernel base table. And from this you find out the particular entry corresponding to P1. For example, this is the entry. Now this value must be loaded somewhere, because this process is active. It means that every time, every access, memory access, this will be used. Okay, so this will put into register, and now using the register, this gives a starting address, and okay, and then you simply do addition to this with VPN number, and you get a particular page table entry. Okay, so there is a, so basically this page table. Okay, that this is okay. Uh, so this is the responsibility of OS to keep this kernel page table. Okay, it corresponds to number of active processes at that point in time, a number of processes that are alive. All right, so please go through these slides all over again. Okay, and if you have confusion, please let me know in the next class. But it's very important that you read this. Okay, also go to book and read, because what we have covered in just 1 hour is there in the book in 30 pages, right? So you'll have to read it whenever you have time. To summarize, user has, or program has, its own view, like we have seen, all this starting from 000 to whatever, which college this corresponds to virtual address or address space. Okay, and it has a view of contiguous memory. Okay, it starts from some set VA. Okay, and so the basically user view is that it starts from some 0000 up to FFFF, and it's very large. Okay, and all right, in reality it's not contiguous memory, because physical memory is limited in size. Okay, and then these pages or whatever it wants, user program wants, can be there anywhere in the physical memory. It means that the page can be placed anywhere, and it's of finite size. Okay, so virtual memory provides us illusion of contiguous memory. All right, and it gives illusion to running process of kind of infinite memory. Okay, it also provides protection. Okay, and the way of to implement this is convert this into pages, and then create swap space as soon as process created, and something that is, and then when virtual address comes, go to page table, see the physical page number, and then use offset and read the byte. If the page is not there in physical memory, the page table entry will show uh, you know 0 entry. Then if it's available in swap space, okay, bring it from swap space to main memory and change the page table entry. That's all. Okay, okay, there are a lot of diagram I have included because it will give you clarity. And next class we will take up some examples and show you how it's happening. Okay, so today what we have covered is actually background. Next class we'll build on to this one, and then we'll try to optimize, because now you know that how many access are there to just simply access uh, you know one address. You first thing is that you'll have to go to page table. From page table you will get address, then you that address you'll have to go to physical memory, and then use offset and read. So many cycles are there, right? Many things are happening. How can you do this within a clock cycle? Where every clock you need to do this in pipeline. Then we have to have smart ways of doing this, and how to optimize this then. And we see the page table alone is 200 2 raised power 20. Will have 2 raised power 20 locations or entries, and each entry will have certain number of bytes. So it means that your whole memory, a significant part of memory are you using just to keep page table for each process. Okay, these answers possibly will have in next few classes. All right. Okay, bye. See you tomorrow.